Yeah, so today we're going to bust out of our 3D constraints and go to kind of arbitrary dimensional visualization and how do you kind of figure out how to embed it. So it's interesting, there's the visualization conference, and then it was InfoVis came on, and then they split off SciVis, and then I think of SciVis as three-dimensional embedded visualization. I think of InfoVis as strictly more challenging than SciVis because you first have to do the embedding and then you have to figure out how to display everything. It doesn't make me popular among my colleagues who just want to say, no, they're different. They're just not the same. All right, so first some examples. Thursday, we're not going to meet here on Thursday. We're going to meet 2 floors up, one half of the building over, same building, but that direction. 264 is in the middle of the robotics lab and the old head-mounted display lab. So you have to go through some other lab to get there. It's very near the stairwell door on kind of either side. You go on through to the middle. 2 weeks. Your presentations are due, not the kind of practice ones, but the actual final ones. Your final write-up is going to be due on the day of the final for the class. And so the thing you present in orally, I'll give you some feedback on that. That won't be the final grade for some of it, but it will be your whole 10% presentation grade will be from that day. And then you kind of have a rethink and submit for the final exams. Has everybody completed their goals? I know of 2 teams' goals that I started out with or sent me one. I haven't seen the goals. I'm happy to reiterate on the goals for the other groups. You don't have to, but I'm happy to do that for you. Have you iterated your designs? Right, so you probably want to be thinking about do the whole design, think about it, try again. Are they better than the best homework design? Right, that's a good watermark to have. All right, so today we're going to go basically beyond 3D spatial embedding and try to understand how do you visualize data set that is high dimensional, that is graph-like, that is not embedded in 3 space.
Sorry, can I just ask a question about that? For the final presentation, are we supposed to have our implementation finished at that point?
Not necessarily.
Okay.
You mean the in-class presentation?
Yes.
Right, not necessarily.
Okay. But it has to be finished by the time we submit the report?
Yep. Excuse me. All right, so the key challenges there are basically, I'm not going to show you all the information visualization techniques. There's a whole class you could teach on information visualization. This is kind of the one sliver we're going to have through it for the class. So key questions for me are how do you embed this data from high D into 2D or 3D? How do you reduce high dimensional data? So in other words, there's kind of the dimension that it lives in, and there's also kind of number of values. We looked at multivariate visualization before. This is kind of multidimensional visualization, and how do you convey relationships. So as with scientific visualization, the choice of embedding depends on what you're trying to answer, right? And so you can play some tricks that will show some things and hide other things. And that's your only choice, because you're strictly losing information when you kind of come down from other dimensions. And there's often, the embedding will change to different level of details, and focus of context techniques are there because there's so much data, you can't really put it all on the screen, right? If you have more than 1 million data points, you're not going to have a good time putting it on the screen. So starting out with thinking about focus plus context, this is also true in scientific visualization, right? We've seen this in some of the homework projects. You may only want to show part of the data in detail, but you also want to know how that detailed data relates to the rest of the grouping, right? Is this kind of 1% of the data? Is this 90% of the data? Are the rest of the clusters laid out similarly to this one? Are they different? And so basically focus and context try to do that, and where they dedicate some screen space to part of it, and then they kind of move everything else to the side. Interactive analysis is basically something we've seen in the homeworks as well. Is you always wanted to be able to zoom in and decide where you're going to go in on the data sets. Also, you can do results of queries, right? Where is it? Mine for me this data. Where are things that I might want to look at and show me what's going on there. Find me areas where there's high correlation and show me those particular areas. And then our pattern detection, as we look at it, can look at subsets of data. And so this basically lets you ask one question at one time, a different question at another time, by either remapping the way things are into space or kind of zooming in on different areas of the data set. All right, so first we're going to look at some techniques for small data sets. And so this is basically a group that took, kind of the Tufte-Menard poster that showed going to war against Moscow and coming back, Napoleon's march against Moscow, and tried to apply it to other things. And so this is basically flow maps, and so it's how various things flow across the maps. And so line thickness here indicates kind of how much wine was exported from France to the rest of the world in the left map. And an artist generated the kind of representation on the left. And on the right, you see an output of an algorithm that's kind of trying to generate these maps automatically. And that data is migration away from California from 1995 to 2000, right? And so, completely custom, same technique, and then more automatic, similar technique.
Wow.
So cartograms is a way of trying to show data on maps, right? There's values and there are different locations across space. They show how important each subdivision is in terms of some kind of information of interest. And so the map at the top of this slide partitioned into states on the left and counties on the right. The color map depicts the population in each state. So the population in the state doesn't really have anything strictly to do with its size, and so you kind of get a misinterpretation of that. And so on the bottom, they're arranged by population, right? And so an awful large fraction of the country lives in California. An awful large fraction lives in LA County of California, and then another large population lives in New York, right? So this is why we see a lot of politicians perhaps focusing on, California and New York. And this is basically scaled the areas by the data and also colored by the data.
Did they determine the height and width?
So I don't know how they determine the aspect ratio. I mean, they're trying to match the same layout that they had up here, right? So they kind of keep the same, layout and try to, minimize distortion, I would guess. And so that's how they do it that way. All right, so here's another way of doing the distortion. And so this is basically net emigration over the last 50 years, right? And so on top is how many people emigrated by kind of color, and here they distorted the shapes. Here they didn't turn it into blocks. They wanted you to keep the other overlying shapes. And so, people are not emigrating from the United States, and so it's disappeared, right, in the map. And so you kind of get this interesting, draws your attention to the places where the data is highest, still has some idea of, what the layout is with respect to continents. If you knew ahead of time that these were continents, you could probably figure out which one was which. And so it's trying to kind of walk between those. And the country colors are mapped through a rainbow color map with 12 colors going from rich to poor. And so they're basically a discrete use of the rainbow color map. All right, so here's a way to show information about events that happen at various times. On the left, you can see that there's a map of the world with a plane at the bottom of the image. And above that are dots that represent outbreaks of avian flu. And the vertical position of the dots is the time when the outbreak occurred. Higher means further in the past, right? So you can trace kind of the original occurrence and how it went from place to place going down. So vertical drop lines tie that to locations because there's a confusion about Z and kind of X, Y as we're looking at this projection, so that lets you know kind of actually where this is in space. And the horizontal lines depict movement of individuals with the flu across the globe. And so this is showing from place to place. On the right, we don't see the horizontal lines, but the spatial embedding is the same. And color here indicates the species that was infected with the flu, right? And so you can try to see it was over here, it jumped species, it went over there, and kind of understanding how this spread across the globe. Here's another image from the same paper that showed how these relate to major flyways for migratory birds, right? So one hypothesis you might have is that bird migration is the cause of this, and this lets you kind of test that hypothesis, and it seems to be going kind of perpendicular to the migratory paths for large things, but over here, on the right, it's kind of staying within this zone, so could have been one. All right. So another approach is to look at multidimensional scaling. And so basically the approach here is a family of algorithms that take things that are close in high dimensional space and leave them close in the projected space, either 2D or 3D, and things that are far away in the high dimensional space end up far away in low dimensional space, but there's no other relationship. It does not try to kind of keep spatial layout in any way. It's basically, you can think a little bit about this as tying springs between all these points and then flattening them and seeing where they end up. So it's basically doing an optimization routine. If you flatten at a slightly different direction, you could get a completely different layout. If you had slightly different, original positions, you could get a completely different layout. And so one of the issues is actually to figure out how to make them stable as you add points. And so there's actually algorithms that are incremental algorithms or that will average over time to try to keep things from completely jumping around as you add points, but that's the basic idea. All right, so H blobs is one way to do multi-dimensional scaling, and so this is hierarchical blobs, and so this is basically the same data, but the blobs are kind of around higher and higher isodensity surfaces, right? And so we're basically saying at large scale, here's where the data lives inside. If you look at a higher surface, now we start to see a couple things in a larger blob and one point off to the side, and then more detail and more detail. And so these blobs are enclosed by these, enclosed by these, which is enclosed by these, is the idea. So this doesn't really show the value of the data in individual clusters, but it shows what the layout is, and if there were groupings that were very close together, they'll persist all the way kind of up the hierarchy as a high density region in space.
So what's the range of the blobs? So like, is it like, oh, this blob has 5 things in the cluster, and then the...
So it's more like you take the data points, you splat them with the Gaussian into a 3-dimensional volume, and then you do isosurfaces in that volume at different density levels. And so it's basically coming in from something that includes all the density to something that includes less and less. It has to have more local density to kind of persist across.
Are the specs there, the data points themselves?
So these specs are little sphere. So the specs here are the data points themselves. That's right. And then these are kind of, there's little, bounding round things around them that are ones that are left out of the clusters that don't land in any clusters. This is kind of a similar example, but instead of in 3D, it's in 2D. And so this was basically the topics that were presented in SIGGRAPH and kind of how close the papers were to each other in terms of text analysis. And so this is basically laying out the papers in terms of their differences in kind of the number, kinds of words that they used in the fields. And then they, just for fun, picked out individual peaks and kind of looked at the papers and tried to name what it was that these papers were about. And so molecules were this big peak up here, and because of the kind of quality of this rendering, I can't read really any of the other peaks here. Right? But this shows you kind of, there's also using the black body radiation, the blue body radiation spectrum to go from blue through red to yellow to white, and so you can kind of see where the height values are, even though the height field is pretty hard to understand because there's a black body radiation coloring. You can at least see kind of there's a high peak. It's about the same height as this because they're both yellow. All right, another large group of information visualization categories is tree visualization. How do you visualize data that forms into trees? And so we'll talk about what's a tree. So the trees model hierarchical information really well. Every object then goes into 2 children or some number of children. Many structures are, in areas, corporate management hierarchies like this, governments are like this, taxonomy, data structures. And so there's a lot of techniques been applied at that. We're going to look at several of those. So kind of the basic way to draw a tree is, so a tree is basically a graph. It's got only one path from any node to any other node. And so a node is kind of represented here as a dot, and then a line shows you a connection between the nodes. On the right, a graph is a generalization that can have any number of links between any of the sets of nodes. They can be completely connected, or in this case, just partially connected. And so we'll start out by looking at tree visualization, and then move on to graph visualization as another set of techniques. So in general, node link diagrams can be more complex than the simple examples I started with. So Colin Ware's book, figure 633, shows a visual grammar of node link diagrams that gives you an idea of how different shapes, textures, colors can be used to put these together in interesting ways. And I cited here to point out various ways you can use to convey the information within the graph, which you can then apply these techniques to the things that we're going to see coming next. All right, so cone trees is, one problem is in 2D you quickly run out of space. Lines start to cross, you can't put all the points there. So this is an attempt to put the thing into 3D, not necessarily that you can see the whole 3D structure at once, but you get an idea of the layout and then you can rotate around to zoom in on the particular place that you're interested in. And so this is kind of a vertical version of that. There's shadows that kind of show you where these things go down, and this is a kind of a horizontal version of that with things that you can rotate in the front and see how many things there are.
What are the little label-y things on the sides?
So this is looking at, this is kind of a GUI that they put in this. It's a search. So you can search in there and it'll swing the thing around that you wanted to see to the front. And this is kind of showing you kind of standard this to this to this to this to this node is kind of the one that you're tracing along the front. And they kind of put them on the sides.
Okay.
Shadows to me are a little bit more helpful here in this view than in this view. It gives you a good, different viewpoint.
Any tools out there for automatically drawing those?
There's less tools out there for InfoVis than there are for SciVis. There's starting to be some packages that you can use to do that. You can look in the paper and do a kind of a sightseers, forward references, and see if there's anything out there. I'm going to show you some examples of InfoVis packages, but note that particular one is in there. So this is basically a diagramming a sentence and try to show you salient features of the text, and there's kind of various level of details in the text as you group things up. So kind of all the characters in the word group to a node at the second level, and then they group the words together as they're more grammatically similar to give you an idea of kind of how far up the hierarchy you go before you get to these two similar ones. Now, as long as the tree isn't too large, you can start to understand that. But as you get it too big, these tubes will start to overlap, and the tree is going to be more difficult to understand. So there's some nature-inspired graph layout, and the question is, how do we kind of have fairly complicated structures that lay out and nonetheless don't overlap with each other? And so they looked at inspiration from sunflower seeds and to figure out how to pack the nodes into a tree. So in this case, there's no optimization required to determine node placement because it's basically a recursive formula. And so you're basically putting it in. Now, you may not have all the nodes filled, and so you may have gaps in here, but you don't, a lot of the algorithms we're going to see, you basically have to try a layout and then do some force-based adjustment to try to optimize that. Here, things will stay put and they won't wander around as you add new elements and take elements away. So hierarchical clusters, and so this is basically similar to the H-blob, but this is taking kind of arbitrary data in, maybe text data, maybe other data sets, and saying these are close to each other. And then the next level up is closer, and the next level up is closer. Some of this is similar to work that we see in DNA, gene sequence analysis, kind of which of these things are similar to each other in response, and how can we cluster them together. At higher levels, you reduce the level of similarity in seeing that. So basically, you're choosing a tolerance of how close two entities have to be considered part of the same cluster, right? And so here, that's the level that this happens at. Say at this level, these whole things become one cluster. At this level, these, the yellow is one cluster and the blue is another cluster. And so the level at which they group together is seen in this display as well. Hyperbolic trees is try to deal with larger ones, right? So here in the case, what we do is we change the zoom at different locations of the image to be different. So in the center, nodes are fairly far apart. You can see the labels pretty clearly. As you go out one node, there's a ring. As you go out to the second thing connected, there's another ring. And the zoom level gets higher and higher as you go out. And so basically you can see pretty clearly one node and its neighbors, maybe its next neighbors, and after that it's just kind of the density information about what's going on. Now as you click on different nodes, it smoothly goes to put that node in the center, and so you can maintain context because of the smoothness and still kind of understanding what the relationship is between those nodes. So you can walk all around this tree by clicking on different nodes, and it goes to the center, to the center, to the center. If you don't have smooth animation, which we don't have here in these four images, it can be hard to figure out, wait, which of these nodes is the one that matches the one I was just looking at? And the animation helps with that a lot. So another way to represent trees is with tree maps. And so this is, basically a rectangle represents this entire subtree, and this is using colors to help group, give you an idea of which rectangles group together. And so you can subdivide the sub-rectangles in order and the importance of the subtrees. And so this is often done for example, looking at the hard drive, file size, right? And so there's several examples we'll see of that, where you kind of got one directory with one giant file in it, directory with 3 medium-sized files in it, you've got another directory with 2. Now here, this is some optimization that's done the layout. It hasn't particularly tried to preserve aspect ratio, and so some things are tall and skinny, some things are blocky, not because they're trying to tell you anything about those, but that's just how they pack the space efficiently. So there's many levels in the tree. You can get a whole bunch of small rectangles. It's hard to see what's going on, and the color coding helps you some with that.
Wow.
All right, so this is actually was used as part of a product to figure out, when you wanted to trade, buy, and sell in different markets. And so here, there's large, the energy market, capital goods market, healthcare market, financial market, and this it's overview of the stock market over time. And there's different sectors. So the area of the sector shows their importance relative to the value of the entire stock market, right? So kind of how much of the entire stock market value is captured in this sector. And then each is subdivided into smaller rectangles that represent individual company stocks in that sector. So color indicates whether the stocks are rising, falling, or staying the same. And so there's actually a different color encoding if you're red-green colorblind. They realize that this won't help you if you're red-green colorblind. It does help the rest of us, so we're going to leave this as default, but you can pick one that doesn't have this. And so kind of intensity so color green or red shows rising or falling. Saturation shows the amount that you're rising or falling. And then the size shows the actual value. And so it gives you an idea of how things are changing over time. So cushion maps has this interesting multiple level of detail, and they use lighting to make the groupings, right? So this makes it does a simulation of illumination, where basically it's a diffuse illumination with the illumination coming from above. So as you get away from the lights, you get darker, and so you see these sharp boundaries between things, and the height of the cushions gets kind of fractally smaller. So as you get, new level, new level, new level, it doesn't come up as much above the ground. So you get these kind of darker, very clear boundaries around larger groupings, less dark around next boundaries, less dark around next boundaries, and so you can, and these, cushions are kind of little quilts on the bigger cushion, right? So the overall shape is of the outer cushion, and there's little sub, kind of quilt areas in that, and little sub quilt areas in that to try to give you a separation on this. All right, so here's a kind of a combination tool showing you color and cushion maps, and you can kind of click and drill down and see graphs of the different approaches. This is again a hard drive. What's going on in my hard drive? What files should I delete to make things work? And you can actually maybe you still can get WinDirStat, which is basically an application to do this. All right, so this is basically an approach that tries to, instead of making everything squares or rectangles with different aspect ratios, say, okay, let's actually do this by laying them out kind of with a force-directed graph, and then show you the Voronoi regions between the graphs. So a Voronoi region is basically, if you have points in the space, the Voronoi region of a point is the region of space that's closer to this point than any other point, right? And so if you bisect these points, you start to get the boundaries of this Voronoi regions. And so it basically segments space into regions that are closer to one point than any other point. So then you uniformly do the layouts, and you get a more kind of pleasing to the eye description. And then they do on the right, comparisons with various competing methods. So graph splitting, basically we're leaving our foray for visualization and graphs with this graph splitting approach. And this basically is very similar to the H-blob technique or the theme view techniques. It basically looks at the density of kind of nodes in the graph, and the 2D Gaussian is splattered onto a regular grid, resulting in a 2D density field, and then you apply whatever your favorite 2D scalar field visualization technique is to that density field to understand what's going on with the graph. All right, and so I've kind of scratched the surface of GraphVis. And so even within GraphVis, TreeVis, we're not showing you all the things. There's actually a site online, impossible to read here, blue on blue, that has, this is page 1, right, of this series of images that he's culled from around the network on different graph techniques. Here's, page 2 of that, and I think it's page 2 of maybe 10. And so all the techniques in the world you wanted to go is a link in the PDF file that's the notes to go for this class. All right, so now we're going to switch from tree visualization to graph visualization. And again, we want to show all the nodes clearly and the edges. We'd like to avoid edge overlap, right? It's not possible to overlay every graph into a plane without overlap, but you'll try, you can try to minimize that to some extent. All right, so here's the airline flight network. And so this is basically showing airports visited by the Czechoslovakia Air Transport Company. And so this comes from Edward Tufte's book, Envisioning Information, that we'll touch on at the end of the lecture. You can see a couple features in the graph. Circles represent airports. Sizes of the circles indicate the size of the airport. Lines connecting them represent direct flights between them. And multiple lines between airports means that there's multiple flights per day between them. So you can kind of see how much traffic there is between each pair. Facebook friend wheel, right? So this is for
Rainbow color map.
Say again?
Rainbow color map.
Yeah, it's actually not. It's actually it's a nominal color map, and so yeah.
Is it?
Yeah. Yeah. Oh, is it not? I was sure that it was, so I didn't put any sad face on it.
Kind of a
So I'm sure
gradient,
it was
though,
dark
isn't it?
blue, purple. Oh, you think? Yeah. But it only counts for this one, not the next two, which are the same.
I'll take 1.5.
Slide.
Color friend wheel.
I looked so carefully, I was so sure. All right. So this is David Fang, who was one of my graduate students who co-taught the course with me a number of years ago. And so this is basically, different applications that you can add to your profile. And this is kind of the friend wheel. So this is interesting because there's different clusters. So there's, family, there's friends, there's people I met in grad school, there's people I knew from, whatever club. And they group themselves into interesting, kind of very highly connected groups that have, in this case, no connections with the other side, right? And so you can see that there's this separate cluster here, but then there's these two folks that actually do cross these connections. Corey Quammen taught the course, a few years after I co-taught the course. Here's his friend wheel. You can see kind of a little bit different. There's more kind of, 3 clusters. There's more people going across these gaps. And then there's my Facebook. Not because I had no friends, but because I had no Facebook. So it's a trivial display. So this is kind of you can do this similar thing with radial focus plus context graph. And so basically you're trying to see highlighting of levels. So again, there's a paper. This is basically looking at a visualization paper and the paper it references. Right, and so the paper itself kind of highlights large. In the middle, you get kind of a picture as an example, and then you see the first references, the most primary references to that, and then the papers these reference are basically just dots around the edge. And so again, you can aim and zoom through, kind of walk your way through this space and look at a body of literature and kind of see which papers refer to each other and which kind of are the seminal papers that everybody refers to. Social network identity resolution, so it's not related to, restricted to friendships. Sometimes this is in cases collaborations on publications. And so one question is, authors don't always have the same, sometimes it's G. Grinstein, sometimes it's George's Grinstein. There's not exact, same replications. So this is a way of helping you walk around and say, okay, was this, do the same kind of people, were they co-authors often in the same paper? If so, it's probably the same author. And it's a way of kind of looking at noisy data to figure out, what's the most likely correlations within it. Social networks over time. So networks change over time, and so people add friends or lose friends. In government structures, officials are promoted to different roles or fired from jobs. And so how you understand how a network changes over time is interesting. And so this depicts the hierarchical social network that is the North Korean government. Right? And so kind of the question was, who's a rising star, who's not to be talked to anymore, who's to watch out for, what's going on. So the top image shows the hierarchy and the results of a query for individuals who at one time were Air Force commanders, which are shown in blue, right? And so there's some Air Force connection going through this whole display. And the bottom image shows changes to the hierarchy from one time period to another time period, which is highlighted in red. And a slider bar lets you show movement in time. And so animation happens between things. So you can pull out, or these are the changes that are going on, and kind of directly make them pop out.
What happens when they die? Because they get killed off a lot.
I guess they're gone from the tree.
They fall down?
I don't know about
Yeah, they turn red. I mean, we're still alive.
So VinStir is another application to show social networks, and is tailored to a particular task. And so on the left, the task is to show all the social connections between two people who are not directly connected, right? So how do these people know each other? And these are all the possible ways they know each other. And they're highlighted, and individuals that are not on the path of connections appear faded out. And on the right, there's various communities. They're shown against colored background shapes that define the boundary of the community. And communityness is a function of a parameter that can be changed in the application, right? You can pick what your communityness calculator is and see how the groupings change as you pick different elements. So the work on this slide is based on collaboration between visualization designers and social network researchers. It turns out that the network researchers are often interested in a matrix view rather than node link diagrams. And so in this system, they actually provided both views tied together so you can see some useful things in the matrix view. For example, tight connections is much better shown this way than this way. It's basically showing that everything is connected to everything except along the diagonal. And it would take a long time to figure that out by looking at this graph. But some of the other kind of interesting star shapes maybe not so usefully displayed in here. In general, the people still preferred the matrix diagram to the node link for this particular one. So this is trying to show semantic relationships. And so the idea here is you use actually brief written descriptions on the link, right? And so if you're close to the screen here, you can see enemies with, and enemies with, and enemies with, right? And so this is not likely to be scalable for large graphs because you have to have text going between this. And then you can repeat the description if it's long enough to go in between there. So the problem with graphs is they get so big you can't see everything, right? And so the question is, what are the kind of primary important features and how can I leave out the details that don't matter? And so one approach is basically reducing the number of edges, but you still want to show between the edges you've deleted what's the relationship between those entities. So here, edges between entities in the cluster have been removed, and a background shape shows that there's a bunch more edges, right, that aren't shown in here, a bunch more edges that aren't shown in here. And it's similar to the VinStir communities. And so here, if you click on a community, it expands to show that in more detail, so you can kind of go out a level and in a level to kind of go into the details that you need. And the labels in the background here are arbitrary, but they could easily be names of the communities, right? They're just 1, 2, 3, 4, 5, 6, 7. So small world graphs. So this is basically showing small parts of a graph. At the top, you see graphs where the nodes are represented by spherical objects. And then the idea is to keep the spheres the same size while zooming in or out of the view. So as you zoom out, the spheres start to intersect with each other. It makes a larger solid geometry that kind of shows how things are clustering, right? And if you zoom in, the spheres separate, giving you the links in between the nodes, right? And so this naturally scales to kind of a blob whose shape gives you the idea, but as you zoom in, you can see the individual details between nodes. And the sequence of images on the bottom, similar nodes are clustered, and a fisheye lens is moved around to expand parts near the lens to show more detail. And so the spheres become smaller when the lens is near and the clustered nodes push apart from each other, right? And so you kind of are spreading out the web and then shrinking it in as you move around the display. So here is a visualization system that shows an overview of the entire graph at the top and a close-up view of a subgraph in the main window. The subgraph of interest in the main window is highlighted in the overview, and a color map shows a quantity associated with each node. And so it's actually a searchable text tree. So on the left, you can just kind of search for a particular text, and that will pick a particular section of the graph, and then it'll be expanded down here. Another approach is to try to make transparency, right? So this is the graph edges will become less and less opaque, and so you can see what difference this makes in this particular example, whereas on the lower left it's kind of completely overplotted, and on the right you can start to see the structure come out a little more clearly. And so the edges in the lower left just form a big blob that doesn't tell you who's connected to who very well in that. All right, so you can also add a probe that will basically create a repulsive force around the edges, and so you can kind of squeeze out the things that you didn't want near there, so you can look at the thing that was behind them. And so this is an example of a probe being used on connections between strongly connected nodes, and transparency can help with this as well.
Do the curved lines make it easier or harder to tell where the goes?
So curved lines, as we learned before, it's easier to follow at crossings what's going on, right? So
Right.
if we have this stuff going on, then everything looks like a crossing, and we have a trouble with this. And so the curved lines, I think, help with understanding those. Also shows you some common fate things. All right, and so this is basically some graphs is just there's no hope, right? If you just show all the lines in the graph, no matter how translucent you make them, you just get a big blob. And so here you have to reduce the edge count drastically, but you still want to preserve some important edges that capture overall structure. So now we're in the case where you had to kind of define what did you mean by important edges, and so this is going to be kind of a task-dependent approach. And so this is a graph of the internet, 2004. And this is basically a blob of edges. And so the middle image shows a graph topology reduction technique applied to the graph. And you can move a probe around the graph, increasing the resolution near the probe, and removing from the graph near the probe location. So basically the red is kind of a focus area, and a bunch more lines show up near there. All right, another edge reduction technique that looks a lot like visitors' communities. At the top of the image, all the links within the community have been removed, and only links between communities are shown. And at the bottom, edges in a click, or which is a subgraph where every node is connected to every other node, have been replaced with a star glyph, right? And so basically, instead of saying everybody's connected to everybody, you just put a star there and lets you know what this means is everybody's connected to everybody. All right. So now for something completely different, parallel coordinates, which I think we've seen a couple times in examples from David Feng's work. So basically the idea here is highlighting high-dimensional information, and so we're going to kind of go in depth on different techniques that people have used for parallel coordinates. So once again, so this is the kind of the car data set, which is one that always shows up in parallel coordinates data sets: miles per gallon, cylinders, horsepower, weight, acceleration year, and kind of where it was. This is one particular manufacturer highlighted here. There's light green lines showing the other manufacturers. So every car is a line that goes to one point on each of these coordinates, right? And so that line tells you its value in all these spaces, right? So, tracing things
Good luck.
is easy between neighboring ones, but if you have to go from this end all the way over, it can be more challenging. So often there'll be reordering that you can do to the parallel coordinates, so you can put the ones you care about close to each other, and then start to see patterns, right? And selection is often done as is here. You want to just select this manufacturer and see how their vehicles spread out across the whole display. And you can pick a different manufacturer and see how their cars spread out across the whole display as well. All right, so a natural extension to the basic technique is to add color. And so here, lines are mapped to a color that represents the quality of the data for your favorite, for their favorite quality definition. So the green to med color map indicates worst to best quality data. So if you think of uncertainty, you could be mapping uncertainty from red to green, and then you can focus on the data that was most certain, the data that was less certain, whatever your particular interest was. Another extension is to do an opacity map. This is like when we did the graph edges. You can make them a little bit more transparent, and then they tend to blur together into what looks kind of like a histogram, or it looks kind of like a density map. And so basically now you're having a harder time seeing individual lines, but you can get the overall idea of, yes, most of the values are low over here, and they're kind of middle high over in these displays. So it's harder to follow individual lines, but you get a better layout distribution on the individual axes. All right, parallel coordinates over time. So this is very much like a line, just a graph, right? This is if one of your axes is time, parallel coordinates reduces to a graph over time. And so basically this is showing the age of the data by lowering the saturation of the color as the data gets older. And so this is basically a parallel coordinate over time. So the newest data is very bold, the older data is faded away, and so as you're watching values of the whole thing change over time, you get a little histogram of what the last values were on that axis, as well as what the most recent ones are. All right, so if you get too much data, then you're hosed, right? It kind of overplots and you get a big giant black rectangle. And so one solution is to try to algorithmically identify clusters in data and then increase the lightness of those areas, right? So this is, my algorithm has picked out some interesting things and shown how they kind of go across the display. And so combined with transparency, you can show what the algorithm decided were the clusters in the data. All right, so the focus plus context, right? So again, if you wanted to see a whole bunch of parallel coordinates, you pretty much can't see them all, and so this zooms in on ones in the middle, pushes the other ones to the side, and then you can, of course, pan around and decide which section of the coordinates you care about, and reorder to put the ones you care about in the middle. And then this is letting you, again, pick particular values and see how they go across the other, and then fades the other ones into the background. So as we learned, curvy lines are easier to trace than angular lines, right? And so as we go through some of these earlier displays, it can be a little challenging to know which of these lines going in here corresponds to one going out, because there's no way that we would know, right? So this tries to ameliorate this by basically giving them a common, kind of a uniform trajectory as it passes through a given coordinate. So now you can tell which line in here corresponds to which line comes out to some greater extent, to the point where there's overplotting and you're hosed again. All right, and so there's kind of a zoom in on a couple of those areas. All right, another approach is to, doesn't help you with that particular kind of alignment, but it does still give you good continuity. So at least at the kind of sharp edges, you don't lose the continuity. So this is basically going flat every time it gets to one of the coordinates. And so it's zero derivative, not just smooth. And the main benefit of doing this over the other is that it's independent on the two sides of the graph. And so you can actually more rapidly compute this than you can the other. And so you kind of can do each individual segment independently, and as you adjust things, you don't have to kind of take it all the way out to the other one. All right, different approach. Instead of parallel coordinates, this is not orthogonal coordinates. This is just coordinates at different angles around, right? And so this is taking the parallel coordinates, sticking them together at the bottom, and spreading them out into a fan. You can either have a kind of whisker plot, which is just the lines, or a star plot, which shows you the boundaries around the lines as well. All right, so let's do a great thing. Let's combine star plots in 3D to get even more data, right? So here we've kind of gone off the end, right? Because there's so much confusion between X, Y, and Z that tracing anything is hard. There's occlusion, and so you can't tell what's on the back. And so this is a case where it's not inconceivable to me that if you had it floating in front of you and turning it around, you could learn something from it. But when you're looking at a static image, it's not, you can basically put more in confusion than you have. All right, so RadViz, another really cool approach. So the idea here is, I think we can find a video of this. All right, so there's several coordinates, and they're laid out here around the circle. All right, so now a point is plotted the same way you do an orthogonal, right? It goes this much along X, this much along Y, this much along Z. Although here they're not orthogonal. So this point could have a number of possible coordinates, right? It could be just a little bit of blue and nothing else. It could be a lot of blue, dark blue, and white. Or it could be a lot of light blue, a lot of dark blue on the other side. So any of them will put that in that location. There's multiple solutions. But then you can grab these guys and move them around the circle, right? And when you move them around the circle, then all the points follow along. And so you can get an idea of how much importance there was on that point to the ones that... So now you can start to see clusters or things that match a particular data value by moving these around. And if you want to say, well, I want to know something that's either this or this or this, well, you pull all those into the same spot, and now you've basically projected all those into the same direction, and you kind of combine those. And so it's a really interesting interactive way to explore high-dimensional data that lets you kind of track what's going on in different
So they're like
data.
little magnets that either attract or repel.
You could think of them that
yeah.
way. I mean, they're just literally, you're moving the
Yeah.
coordinate direction, and that
Yeah.
shifts to the extent that it has something in that coordinate direction where the point is.
Hmm.
So the coordinate itself is giving the weighting to the following of the display. I've never seen anybody try this with like different frequencies, or sorry, different phases of motion on the different ones to see if you can get anything out of it. So looking for a paper, maybe that. All right. So if we thought that was completely different. So now, situational awareness visualization. So this is basically something I couldn't categorize well. This is trying to say what, when, and where, right? And so when is from the inside out, where is shown on the map, and what happened is grouped into clusters that are not, in this case, a rainbow color map, but actually just nominal colors colored with colors.
Hemorrhagic fevers.
Yeah. I don't want to be there on that map.
So what's the time dimension again?
Plague.
So time is from the inside to the out. So older, I'm going to say without loss of generality, older to newer, where the event happened, and then what kind of event it was. So there's major categories, subcategories, and then your time. So this is trying to show time-varying behavior with flocking boids. And so boids are basically little birds that we simulate that flock together based on rules, right? I want to be this far from my neighbors, I want to follow my guy ahead of me, and they all kind of self-organize into this, and you hope to get some interesting structure out of similar clusters. Fortunately, there's a little unpredictable spatial embedding, and so you're going to have to back out a lot more from the data set. Theme river, right? So this is looking at how popular stories were in the news over time. This was based on kind of original diagram that was kind of the etymology of folk music, right? So it showed kind of where rock and roll came from out of this. This was a hand-drawn thing by a guy who kind of laid this all out. This is kind of an algorithmically generated thing. You can see that, some topic gets much more interesting and then fade off again. And they've shown you particular interesting events up on across the horizontal axis to give you an idea of why these things are increasing and decreasing in popularity. So this is Name Voyager, right? So is my baby name getting more popular? Is it getting less popular? Here it's colored according to boy or girl names, right? And so you can see kind of the most popular names. John becoming much less popular, and so forth. And then there's the bottom one is, still different names. All right, Edward Tufte. And so there's several books in the reading room that I would encourage you to kind of look through. Each has got a really interesting, beautiful example, terrible example he made beautiful, to kind of give you an idea of rules of thumb you should apply. And so there's design guidelines, but there's not a kind of a fundamental theory of how do you apply this. But we'll go through some of my favorites of these. So this is the train schedule in going along one particular train line, right, in France, right? And so this tells you a couple interesting things. One is how fast the train is going has to do with the slope, right? And so if you're asking, if I want to go from Lyon to Paris, well, I'm going to go here. Well, how long will I have to make the next train, right? And you can see that's the gap in the line there. So you can say, well, I'm not going to stop here. Maybe I'll have lunch here because I've got more time in between, and I'll hop on the next train and go this. And so when do I want to come back? So this gives you kind of laid out all kinds of interesting questions you can ask about the data, and it works really great for points along one line over time. This is science. So this is the thermal conductivity of copper, and as it was published over time, right? It's worse than you think. This is a log scale, right? And so, very simple question: how much, what's the resistivity, conductivity of copper as a function of temperature, right? Interesting, behavior of science. Some people published down here. The next folks, presumably got the answer up here, but they're like, oh, we can't say this. They said down there. Well, maybe we think it's here. So quite interesting. So mostly what's going on down here is contact resistance, right? And so it's not to do with the copper. It's to do with the fact that the contacts that you touch the copper with had much more variability than the copper did, and nobody took that into account until more recently, where you do kind of 4-pole measurements where you don't actually measure at the poles, you're injecting the current, and so now kind of here's the commonly accepted value for the thermal conductivity.
Kelvin context.
So his point here is show all the data, right? So if you just show kind of points with standard deviations, doesn't tell the story in any ways interesting. They're almost all below, right? And so you see an interesting kind of distribution. If you can show all the data, show all the data is the point that he asked. All right. So this was kind of chart junk is one of the things he talks about. So in this case, you see this amazing bold grid, moving over space and time, but that's not at all what's interesting in this video, right? What's interesting is how does this cloud behave over time? It's hard to remember how things behave over time, so how about putting in some thumbnails that show you kind of over different times where you are. And instead of the timing, this little ticker that's running around the corner that doesn't tell you a whole lot, you run it along the bottom here. It's a little more subtle, and it gives you an idea of how far you are in the simulation. By the way, there's a vertical exaggeration. We should probably tell you that there's a vertical exaggeration. It's useful to show you the data, but the thunderstorm isn't actually, as many times tall as it is wide. So this is basically the original movie that he saw, and he worked with them to do a redesign of the same data to give a better rendering of that. So one interesting question is, if you're going to put in something, how strong of a grid, right? So a group actually did a study. They did a user study. They asked people too strong of a grid, too light of a grid, just right of a grid, and they tried a bunch of different data sets, a bunch of different layouts, and their kind of basically answer was, is it too high, is it too low, or is it okay? And across a very wide range, 20% opaque was within the good range, right? So if you make your dark lines 20% darker than your bright lines, or your bright lines 20% brighter than your dark lines, across a wide range of sources, that was in the good range. It wasn't always the optimal one, but if you're going to pick one as your default, that would be the one to pick. I love when we actually know the answer to a question. All right, so this is, again, chart junk. And so the picture on the left gives you this interesting couple of behaviors. One is that there's these horrible pins is what you see first, out the ear. The second is these are like call-outs to a legend down below. So then you have to go down and look at the table and then come back. How about if we lighten up these lines and we actually put the labels right here in the diagram so you can see everything that you wanted to see in one description. All right, this is one of the most interesting ones. So this was the chart that the engineers and the managers at NASA had to decide, should we launch the Challenger, right? So this is pictures of solid rocket boosters, not in any particular order. It's got temperatures written on the top of the boosters. It's got damage. Different kinds of damages are drawn with different things on the different boosters. And nobody's name on the diagram, right? This is saying, okay, here's the diagram, figure out what to do about this. So this doesn't show you the thing you care about, which is the correlation between temperature and damage. You have to kind of look around and figure it out. This is good if you're not trying to take responsibility, not good if you're trying to make an important decision. So this is a redesign where you just pick, your favorite value for damage, right? It's not very sensitive to that. And so this is kind of amount of damage plotted against temperature. So this is kind of, something's going on bad as you get colder. This was the temperature when they were launching the Challenger. And so it's pretty clear if you look at it this way, this is not what you want. So this is, one of the reasons when I push on what's the best way to show something, not what is a way you could show something. Right? All the data is here. You could, stupid users should have picked it out. Well, turns out our visual system is not good at answering that question. We're really good at answering this question. And so, what's the best way to show something really matters. And so to the extent that it doesn't matter, why visualize? To the extent that it does matter, pick an effective visualization. All right, that was our whirlwind tour through information visualization. Next on Thursday, we're going to have a lab tour. And then in 2 weeks, it'll be you guys, not 2 weeks, but not next week, but the week after, will be you guys lecturing back to me. Looking forward to see you in office hours or emails about different goals, different designs, and see you on Thursday.